Okay, hi, so in this video we're going to be discussing arc length. This is going to be a very quick unit, and it's going to be very easy as well, so this should be exciting. Let's get into it. Arc length is obtained by summing small segments of a curve using the distance formula. We're trying to find the length of an arc, and we're just going to use the distance formula. Before we get into these equations, let's look at this picture here and try to figure out what's going on. So what we can think about is, let's take any 2 points on this curve. Suppose we want to find the length of this entire curve, but let's just take these 2 points along the curve here. And we can compute their delta x and delta y by looking at their coordinates and computing the differences. And then notice that this is a right angle, so we can form a right triangle here. And we know how to find the length of that red line. We can use the Pythagorean theorem, and that equivalently is just using the distance formula on these 2 points right here. So that gives the distance between them, which is that red line. And then suppose we take 2 more points. Let's say my first point is this blue dot, and then the second point is this blue dot. And again, we can draw these dotted lines here, and again, we can compute the distance between them, like so. And then suppose we take 2 more dots, being this one, and do the same thing. And we keep on doing this until we get to the end of the curve in both directions. You can see that if we sum up these red lines here, we'll get a value that's pretty close to the length of the actual curve, which is good. So we're going to use that to our advantage here. The issue right now of why we're not getting the actual curve is because our points are too far apart, right? If they were a bit closer, we would be better at approximating that curve, right? As you zoom further into this curve, it becomes more and more straight, the closer the 2 points are together. So that begs the question, what if the 2 points were very, very close together? So let's zoom in here. Let's suppose we had this point here and this point here. And we do the same thing where we draw the dotted line, and then we use the Pythagorean theorem to draw the line between them. When they're so close, it literally looks like I drew on top of the arc, right? So now we'll have a bunch more of these pairs of points that we'll have to sum up, which is kind of annoying, but now we have a much better approximation. So what that means is we need to make these points as close together as possible, but they still should be different. They should still differ by a tiny bit of x and a tiny bit of y. So what is this tiny bit of x and tiny bit of y? Well, let's ignore this delta x and delta y, and instead call it dx and dy. Remember, with our integrals, that dx is this very tiny amount on this x-axis, or a very tiny amount in the y direction. So that's what we want, a very small amount in the x direction and y direction. So now, same thing, except now the points are very, very close together. So let's look at the equation and then see what's going on here. So we're using the distance formula, right? That would give us the red line between them. And from here, we can do a little bit of manipulation to the equation. We can multiply this second term by a form of 1. Delta x over delta x is 1, 1 squared is 1. We can bring this delta x squared into here by making this delta y over delta x squared multiplied by delta x squared. We can factor out a delta x squared from this entire thing because it's common in both terms here. So we're left with this product. The square root of delta x squared is simply delta x, so we can bring that outside of the square root symbol. And remember, we want this delta y and delta x to be as small as possible, so we can think of that as dy over dx, which is f prime of x, and we're squaring that. And remember, we're summing up a bunch of these tiny amounts. When we're using a sum, we can think of that as an integral from one end to the other end, from a to b, and this is our equation for arc length. And that's all there is to know. Like, that is the equation. That's all you need to use to compute arc length. In fact, in our problems, we're just going to plug it in and be like, oh, there's the arc length. But what's really important here is understanding how this formula comes to be. So let's take a look at some problems. Find the length of the curve y equals ln of sine of x on the interval pi over 4 to 3 pi over 4. There's a picture if you're excited. There's not much for me to say here besides let's just plug it into the integral and solve for it. So the arc length, which we can call L, is the integral from a to b of the square root of 1 plus f prime of x squared dx. Okay? Our bounds are given to us, pi over 4 to 3 pi over 4. Let's solve for f prime of x. So if f of x equals ln of sine of x, f prime of x, we'll use the chain rule. That'll be 1 over sine of x. We have to multiply that by the derivative of sine of x, which is cosine of x. So this will be the integral from pi over 4 to 3 pi over 4 of the square root of 1 plus cosine x over sine x squared dx. Okay, so this we can think of cosine over sine as cotangent. So this is pi over 4 times 3 pi over 4, square root of 1 plus cotangent squared of x dx. Now, how do we compute this integral here? Well, if we remember some of our trig identities, we should know that 1 plus cotangent of x squared is equal to cosecant squared. So this is equal to the integral from pi over 4 to 3 pi over 4 of the square root of 1 plus cosecant squared of x. Right? And the way we can think of this is we know that sine squared of x plus cosine squared of x equals 1. If we divide everything by sine squared of x, we get 1 plus cotangent squared of x equals cosecant squared of x. I always forget this one, so this is how I would remember it. Another way to get the other identity, you can divide everything by cosine squared of x, and you get tangent squared of x plus 1 equals secant squared of x. I just remember sine plus cosine is 1 and then go from there. But anyways, sorry, this is just cosecant squared here. The square root of cosecant squared of x is just cosecant. So this is pi over 4 to 3 pi over 4 of cosecant of x dx. And hopefully you have this memorized. I often forget it, but this is equal to negative ln of cotangent of x plus cosecant of x, evaluated from 3 pi over 4 to pi over 4. And let's see, we can just plug this into a calculator, and this should be 1.763. So like, honestly, not too much going on here that we don't already know. Like, we know how to compute integrals and stuff. It's just finding the derivative and plugging it into the formula. Like I said, pretty easy. So let's just do the second problem. Find the length of the curve y equals 3/2 x to the 2/3 on the interval 1 to 8. Same idea. Let's compute the first derivative since we'll need it. So if f of x equals this, we can use the power rule to get 3/2 times, I'll just write it out, 3/2 times 2/3 x to the 2/3 minus 1, which is x to the negative 1/3. Integral from 1 to 8, square root 1 plus f prime of x squared, which is x to the negative 1/3 squared dx. We can square the insides. We get 1 plus x to the negative 2/3 dx. And this we can't really solve by hand yet. So you can just plug this into a calculator if you want, and you can get 8.352. So you might be like, okay, that was a boring example, and yeah, it kind of was. But the reason why I chose this example is to see how accurate were we. If we take a look at this line, or this curve here, it looks like a straight line almost. Like if I were to draw this pink line here and extend this down and then draw the right triangle formed, the red line is pretty close to that hypotenuse length. It's, you know, almost identical. So let's try finding the length of the hypotenuse and then comparing the two. So the base starts at 1 and ends at 8, so that has length 7. And the height goes from here, which is 1.5, upwards to 6. So this is 4.5. So that means the length of the hypotenuse is equal to the square root of 7 squared plus 4.5 squared, which is equal to the square root of 49 plus 20.25, which is equal to the square root of 69.25, which I don't remember what it is, so let me just check. Okay, square root of 69.25 equals 8.322. And if we compare that to 8.352, it's pretty similar, so it seems like we did get the correct answer. So I guess that's pretty cool. But yeah, that's arc length. It's a pretty simple section here, but understanding it will go a long ways when we go into our next section, which is surface area. And you can start to think about maybe how arc length relates to surface area. I'll give you a hint. If we're finding surface areas of volumes of solids of revolution, how can we use arc length to compute the surface area? It'll be very similar to how we did disks to find volume, but we'll explore that more in the next video. So hopefully this was helpful, and as always, take care.